ISO 26262 dependent failure analysis DFA using the PSS. Abstract. Dependent failure analysis DFA as a methodology to define the ISO 26262 to analyze the impact of the errors and one shared resource on the other element and find safety vulnerabilities. Coherency is a good example for resource sharing and thus critical for failure analysis. The usability and constrained random generation provided by the portable test and stimulus standard PSS helps with the generation of the DFA. Dependent to failure initiate DFA and coupling factors of DFE. Introduction. ISO 26262 is the adoption of the ICE 61508 to address the sector-specific needs of an electrical and/or electric system within road vehicles. This adaptation applies to all activities during the safety life cycle of safety-related systems comprised of electrical, electronic, and software components. Safety is one of the key issues in the development of the road vehicles. Development and integration of automation, automotive functionality strengthens the need for functional safety and the need to provide evidence in the functional safety objectives are satisfied. With the trend of the increasing technological complex software content and mechatronic implementation, among others, there are increasing risks from the systematic failures and random hardware failures, these being considered within the scope of functional safety. ISO 26262 includes a guidance to mitigate these risks by providing appropriate requirements and process. Dependent failure analysis DFA methodology has been introduced as part of ISO 26262 Part 11 guideline of the application of ISO 26262 to semiconductors to analyze the impact of the errors on one shared resource to other elements and find safety vulnerabilities. Main SoC system on chip SoC designs for automotive applications consist of multiple process cores and IP subsystems that are shared SoC resources such as memory, so the system interconnect IC and I/O subsystems. In this environment, a fault in a shared resources can affect the other element, the shared resource, and causing unexpected chain errors. When such an error occurs in a mobile phone, the problem can be solved simply by rebooting. However, in an automotive environment, such an error can be fatal enough to threaten the driver's life. ISO 26262, however, defines these chain errors and dependent failures and classified them as cascading failures and common cause failures. Cascading failures, failure of an element resulting from a root cause and then causes a dependent failure of another element or element. Common cause failure, dependent failure of two or more elements resulting directly from a single specific event or root cause. Figure 1. Type of dependent failures. Cascading failures, common cause failures. The purpose of the DFA is to find the dependent failure initiator, DFI, and coupling factors that can cause the above dependent failures, and to prevent or control them in advance. DFA generally proceed in the following order. Identifying the dependent failure initiator, DFI, Finding possible coupling factors for each DFI. Confirm the effectiveness of safety mechanism and measure to prevent DFI and coupling or to mitigate dependent failures. 4. DFA. It's necessary to generate DFIs of the various conditions at a desired time point and generate numerous types of coupling factors to identify violation on dependence or strip them of inference. This meant that we need to create 100 of scenarios that combine all of the functions that can be used as coupling factors for each DFI. We, therefore, needed a new and different kind of verification methodology to model and automatically generate these scenarios. We found that the test generation using the modeling approach and constrained random generation in PSS is suitable for generating numerous tests and with different conditions, as in the case of DFA. The use of constraint-based randomization in PSS allows us to efficiently create multiple randomized scenarios in a fraction of time it would take to manually create and maintain a large number of directed tests. The nature of the randomization allows finding bugs even in unsuspected areas, as well as achieve the much better coverage. Functional coverage in PSS can be used to track the verification process and point out areas that have not been verified yet, thus supporting a metric-driven verification MDV approach. An additional advantage of the PSS is the ability to generate executable code for various different platforms, including RTL simulation, and acceleration, emulation, and even post-silicon. We also collected the result of each test run and generate a new form of the failure report, FDR, which was to immediately reflect on DFA. The second, identifying the independent failure initiator. The dependent failure initiator, DFI, represents the root cause of dependent failures in functional safety. In general, DFI is defined as an item that can threaten the independence required between elements. In this paper, a fault occurring in a shared memory area is defined as a DFI and implemented through the fault injection as follows. Uncorrectable ECC error injection. When the process element reads from memory, the ECC check logic can detect an error in the store the values and return an error responding to PE. In general, an ECC bit is calculated and updated when the data bit is written. Written. So backdoor task allows you to directly access the data array inside the memory model to change it consists of a particular data bit. If there is an error data bit that does not match the ECC bit, the ECC check logic will generate an ECC error and reading the data bit. Our test bench triggers such errors by changing memory contents through backdoor interface. As shown in figure 2 below, ECC error injection can be performed on DRAM, L3 cache, and L2 cache, which have a different coherency target. Figure 2 coherency domain. The memory management unit, MMU, translate fault generation. All peers with an MMU look up the page table and share the memory area and read physical address information for address translation. If the contents of the page tables are corrupted, serial translation fault can be occurs in a PE that references the page table. Our test bench manipulates a valid field of the page descriptor to generate an MMU translation fault at the desired time. 자, RAS error injection for CPU, interrupt controller, system MMU. The RAS, reliability, availability, and serviceability extension is ARM's error handling and recovery architecture that's applied from the ARM version 8 architecture. So RAS has its own fault injection model extension that can injection faults into the L1, L2, L3 caches to generate error interrupt. However, this feature is mainly used for software error handling and recovery process verification because it is a fake error rather than an actual error in a cache memory. We reset the core and the clustering the dual RSA coverage process after RSA error injection to verify the effect of this reset process on the currency behavior of the other processor elements. Using PSS, the above fault injection options are modeled as reusable actions. A PSS tool can generate various DFIs with the desired number of faults at a given time. 3. Finding the possible coupling factors for each DFI. A coupling factors is common characteristics or relationship of elements that leads to the dependence in their failure. The following coherence inference stimulus for a shared memory region may be a coupling factor as it causes different PEs to continuously access to a shared memory region. This results in a dependent failure from the previously defined DFI fault injection into the shared memory region. The force sharing access. The figure below shows the transaction flow when the different coherence masters write their own data to a memory area allocated in the one cache line, 64 bytes. Each master uses a unique address ranging within the same cache line. Each time a coherent master writes a value to a block allocated to it, a number of smooth transactions are generated between the coherent masters to clear the caches of all other masters, as shown in figure 3. If a fault is injected into 64-byte cache line, this coherence operation causes a failure in all coherent masters participating in the force sharing scenarios. Figure 3, force sharing with write competition. Distribution virtual memory, DVM transaction broadcasting. So DVM is a transaction generated by a processor for maintenance of a virtual memory system such as a MMU. As shown in figure 4, when cluster 0 sends out a DVM request transaction, the DVM controller sends a request to the MMU element of the system. When the response arrives from each test MMU and the DVM controller sends a response to cluster 0. The DVM transactions are created doing the address remapping of a recovery process to a fault in a shared memory at this time. If a specific element enters a reset state due to another failure, it may fail to return DVM response and lead to a recovery failure. The figure 4 DVM transaction flow diagram. Exclusive access. When a PE attempts to perform an exclusive access to an exclusive target region, the global exclusive monitor on a system bus allows only one PE, CPU CL0 in figure 5 below, to access the region. During that time, the exclusive target region is locked and the other P's that attempt to access it are blocked until the exclusive access is complete and the lock released. If an error occurs in an exclusive target area during exclusive access, the blocked P's may wait indefinitely for the lock to be released. Figure 5. Exclusive access flow diagram. In addition, CPU cluster power down and dynamic CPU clock level changes also use the coupling factors that can cause hardware coherency protocol errors. The PSS model allows us to create a coupling factor scenarios and inject an error per selected DFI while in parallel running interface stimulus which might interrupt the recovery process. 4. Generating the scenario using PSS. PSS allows you to create all the requirement infrastructure below, but you can also save some time and use an existing library as we did. Among other topics, the library provides built-in actions to generate coherency scenarios for multi-core systems, such as force sharing, truth sharing, RAS error injection, and more. Our project-specific tasks leverage the built-in actions and add additional system-specific contents. A. Traffic generation. Consider, for example, the following system-level scenario we would like to generate. The run force sharing scenario with 85% of the cases do read-increment-write actions. 15% of the cases do an error injection action. Selecting from these kinds, RAS error, an NMU transaction fault, an ECC memory error, or CPU internal exception. The code example in Figure 6 shows the declaration of a new PSS action which selects either valid effect or injection of one of the several error kinds. So the PSS tool will randomize the selection of one of the choices. Each time the action is traversed within a scenario, the action shows the use of both library contents as well as project-specific actions. Figure 6. Activity selection. The code example and the Figure 7 illustrate the use of the utility action shown previously by embedding it within the force sharing action provided in the library. Figure 7. Force sharing with the error injection. The code example above shows the use of template types defined in PSS 1.1. The Figure 8 shows a sample generated scenario in the form of the UML diagram produced by the PSS tool. It illustrates the steps performed by two cores, each reaching a point where it injects an MMU page fault. This is a Figure 8 UML diagram of a generated scenario. Library actions such as the force sharing shown above handle many aspects that are vital to generate a valid system level test. These aspects include core selection based on a system configuration tables which lists existing cores and their attributes, synchronization point between the activity of multiple cores, memory management and memory allocation based on a system configuration table which lists existing memories and their attributes. Using similar combination of library actions and our own project-specific contents, we define even more complex tests such as the following shown in Figure 9. Run the above force sharing scenario with the fault injection. Concurrently run interference scenarios, clock frequency change, powering cores down and up, and exclusive access. The figure 9, force sharing with error injection and interference stimuli. This results in significant and randomized scenarios that exercise many aspects of the system and thus improve coverage and the chances of uncovering bugs. Figure 10 shows the UML diagram of the one such generated scenario. Figure 10, generated dependent failure scenario, force sharing, RW increment, error injection, interference, and power down, and exclusive access and frequency change. B, self-checking and coverage. When using a constrained random approach to additional element checking. First, number 1, self-checking to allow the test bench itself to determine whether the test passed given the randomized scenario. Number 2, coverage selection to record what combination or flows were actually exercised and which are still pending and covered in the verification plan. The self-checking aspect is built into our PSS model and the library. For example, all data that is written to memory is also read later during the test to make sure it is valid. Similarly, PSS functional coverage is used to record the relevant traffic attributes, along with information such as which combinations of error kinds were tested during which types of valid activity scenarios. The following example shows a PSS coverage group definition. Figure 11, PSS coverage definition. A sample coverage report is shown below, illustrating the cross coverage with item with some of its bins. Only few of the bins are shown as covered based on the data collected in a single run. Okay, this is figure 12, sample coverage report. Using the randomized and combining the coverage results of the multiple runs allows us to cover all the relevant coverage goal. This is a significant time saver compared to the manually creating and maintaining over time a large number of directed tests to achieve the same level coverage. 5. Fault tolerance report FTR generation. Fault mode and effect analysis FMEA determines your possible ways a system component can fail and determine the effect of such failures on the system. The DFI thus is selected based on the predefined FMEA items as shown below. The number 13, failure mode and effect analysis FMEA example. Once the DFI is determined, the PSS select an interference stimulus, which can be a coupling factor to create a dependent failure scenario. Each scenario prints out the following information when a simulation complete. Injection fault information. Show which types of the fault were injected in which address. It also shows the time when a fault was injected and the time when coverage process was completed. Executed in the interference action information shows which interference actions were performed to delay discovery process after fault injection. Another error injection can also be used as an interference action. Maximum fault tolerance time interval, FTTI information. FTTI is the time taken to recover from an uncontrolled state due to a fault. The maximum FTTI can be measured for hundreds of fault conditions generated by the PSS tool to determine which coupling factor affect the recovery process the most. The external recovery monitor provides recovery monitor information for situations where the system failures to recover from the generated failures. The PSS tool generated error handling scenarios with hundreds of different conditions, and by gathering the above information printed for each scenario, we created a fault tolerance report, FTR. The figure 14 generated a fault tolerance report. As shown in the figure 14, the FTR provided information to identify which interference stimulus inferred with the recovery operation and the fault injection scenarios where the maximum FTTI was measured. The FTRs for each error generated in this way are reflected in the DFA result as shown in the figure 15 to prove the safety is guaranteed under various error conditions. The figure 15 dependent failure analysis FDA report include FTR information. 6. Results and lessons learned from an actual project. In this paper, we performed the DFA defined in ISO 26262 at the simulation level for the effect of the coherency on the system when a fault occurs in a shared memory region. Through this, it was possible to systematically analyze the possible dependent failure and prepare the safety specifications. We found that this requirement analysis and verification methodology introduced in ISO 26262 can be usefully applied to the general SOC verification process as well as functional safety. The PSS model reusability and constrained random test generation made it easy to generate tests with the various conditions defined in the safety requirements. We find PSS to be an homogenious methodology for reproducing any particular target conditions. These advantages will make PSS an essential methodology for safety verification. 7 is acknowledgement. The work described in this paper was done using a Cadence perspective system verifier and the built-in system modeling library SML. We also used Cadence vManager to manage and analyze the simulation result. Okay, there are so many references. Okay, I read today the ISO 26262 dependent failure analysis using PSS. Thank you for your time and see you next time.